Okay, so last time we classified ADE types, modulo, and assumption. And I'll just rush through the last ones. So I'll just finish the classification, but I'll just sketch it and won't tell you how to classify the ones that are non-simply laced, because it's just a combinatorial argument. But the first thing to notice is that so there aren't the only Dinkin diagram with the triple edge is G2. And that's very simple. So that one we can do quickly. And it's as follows. So suppose that you had other diagram. Oh, by the way, the only connected Dinkin diagram with a triple edge is G2. So this is G2. And let's suppose that we have some other diagram. Since it's connected, then at least we're going to have some other node that is connected with some of these two nodes. So it could happen that it's connected with both of them. It could happen that it's connected with some of them. It may have several arrows. So let's say that you have A arrows here and B arrows there. And I don't care if it's like this or if it's like this or the arrows are in the other direction. The whole point is that if you have a Dinkin diagram that is an extension of G2, it's going to have one node that is connected with at least one of these two. So that means that A and B, one of them can be 0, but not both of them can be 0. So the matrix, the Cartan matrix, by choosing those three nodes would be the one for G2, which is this, and then extended by, well, this guy A would be something like A prime. These are negative non-positive numbers. And then this guy for B is going to be B prime, where A is bigger or equal than 0. And if A is 0, A prime, well, if A is non-zero, then A prime is non-zero. And B is bigger or equal than 0. And if B is non-zero, then B prime is non-zero. And also, we are saying that this is connected, so A times B is not 0. Oh, sorry. Then either A is non-zero or B is non-zero. But both of them are not 0 at the same time. So let's compute the determinant of this thing. So this accounts for all possible ways of joining these things. And the determinant of this thing, well, let's just compute it. It's 2 times the determinant of this matrix, which is 4 minus BB prime, minus, so that's a plus 1 times the determinant of this matrix, which is, well, it's going to have a minus sign anyways. So it's minus 6 minus BA prime. Then we have plus that, so it's a minus A times this determinant, which is 3B prime plus 2A prime. So this is 2 times 4 is 8, minus 6 is 2, minus 2B prime minus A prime B from this, minus 3A B prime minus 2A A prime. And we see that if A is non-zero, so either A or B are non-zero. So if A is non-zero, then this is negative already. And if B is non-zero, then, well, this is negative already. Okay, so if B is non-zero, then this thing is non-zero. And if A is non-zero, then this thing is non-zero. So this is less or equal than 0. So this can't happen. So the only ones that we haven't ruled out are diagrams where we have arbitrary connections, number of double edges. So that's the next step. So the next step is to say that there aren't two there aren't cycles. There aren't cycles. There aren't cycles on a Dinkin diagram. And this, I'll leave it as an exercise on how you prove it, so, but let's sketch it. So there are operations that we've seen. One of them is this thing that if you have a Dinkin diagram, say that you have a Dinkin diagram like this, whatever we suspect that it's a Dinkin diagram, then what we can do is remove some nodes. So we take this node, and we take them out, and remove all edges that come from those nodes. So this edge is gone, and this edge is gone. And the operation gives us this diagram that is just only these 4 nodes. If this was a Dinkin diagram, then this would be a Dinkin diagram. And this operation that's something very simple to see at the level of Cartan matrices. This corresponds to, well, we have some matrix that has 6 entries, like 1 up to 6. So this is a 6 by 6 matrix, corresponding to these 6 nodes. And removing these 2 nodes and the corresponding edges means, well, we found the corresponding 2 columns and the corresponding 2 arrows for each one of these 2 nodes, and we remove these things. And this, what's left out is the 4 by 4 matrix that corresponds to the remaining arrows and rows. Now, the properties of a Cartan matrix were that the diagonals were 2. The diagonals of this matrix are the same as the diagonal of this one, so they're 2. And this non-negativity of the off-diagonal terms, it's just the same for this matrix and for this matrix. And the fact that the determinant of this guy is positive and all of the principal minors of this one are positive is trivial because the determinant of this one and the principal minors of this ones are principal minors of this one. So it's easy to check that if this was a Cartan matrix, then this is a Cartan matrix. So something similar to this is a different operation, but it takes some work to do at the level of Cartan matrices. But the exercise is that if you have a Dinkin diagram that is an allowed Dinkin diagram, whatever the Dinkin diagram is, and you have 2 nodes that are joined by 1 arrow, let's say this node here and this node here, then what you can do is remove the edge and join the 2 nodes. So these 2 nodes you identify, and you're left with something like this. And the exercise is check that this operation takes a Cartan matrix into a Cartan matrix. So it takes, or equivalently, it takes Dinkin diagrams into Dinkin diagrams. Into Dinkin diagrams. So again, it's something simple about like checking about determinants, that the corresponding determinants remain positive. So once you've done that, then it's easy to check that you don't have any cycles and you don't have any diagram with 2 arrows. So there aren't cycles. So you check that there aren't cycles. And you check that actually you check something stronger. There aren't more than 1 double edge. This is very simple. So once you prove that there aren't cycles, that you check in this form. So how do you go to check that? Well, if you had some cycle, so we know that we don't have any triple edges. So let's suppose that there is some cycle like this, and we've proven that there is no cycle which is single-edged, because that's the extended diagram for AN. But you may have some double edges here, and let's say some other double edge here, and so forth. Then by using this second rule, you can remove all of the ones that are simply laced. And then you end up with a diagram that is like this. So you're going to end up with a cycle, but all of the possible edges that you can have are double. So you need to check only that this diagram is not possible. So there's no cycle where all of the arrows are doubled. And that's very simple, because such a diagram would be something like this. Or possible transpositions. And the determinant of this thing is negative. So once you know that there aren't any cycles, you get rid of this. So now you look at diagrams where there are no more cycles, but there might be trees, and some of these things might be double. But then again, we rule out these things by looking at, well, you cannot have two double arrows because you look at the subdiagram like this. Actually, you can stop here. And you find the extended diagram of Cn, or perhaps a transposition. This was the extended diagram of Cn, and the determinant of this thing was 0. So you get rid of more than one double edge. So now you know that there's only one double edge. And if there's only one double edge, then you get rid of that one because you compute explicitly that that's going to be F4 extended. And you compute explicitly the determinant of that matrix is 0. And you're left with only the possible cases that are the ones that we know. Bn, Cn, and F4, which is new, which I think Jethro didn't tell you what this diagram is, and I won't either in the interest of time. But you can look it up in the notes. In the notes, it's explicit what is the Dynkin diagram of F4. Well, the Dynkin diagram is there, but what is the root system of F4? If we have time today, I doubt we'll have time. I need to prove a different theorem today, so I'll prove today Chevalet's theorem. So the upshot is, after this sketch, these are the only possible Dynkin diagrams of semi-simple algebras. Moreover, there are some isomorphisms between them. Let me just remove the extended part of this. So AN exists, and we know that this is the Dynkin diagram of SLN plus 1 for every n bigger or equal than 1. Now Bn and Cn, this one requires two different roots of different length, both of them. So they don't make any sense for n less or equal than 2. But what is clear is that Cn, C2, is isomorphic to B2. This was the two diagrams that were just simply rotated like this. So this is B2, and C2 was the same thing rotated and scaled. So we consider Cn with n bigger or equal than 3. And C2 is just the same thing as B2. And Dn requires at least 4 nodes. And, well, these 3 guys are the same, and G2 and F4 are exceptional. So these are the 5 exceptional Lie algebras, and we have these 4, this A, B, C, and D, which are infinite families of Lie algebras. Now, this gives you some isomorphisms of Lie algebras that if you haven't checked them already, that's a nice exercise to explicitly find them. So Cn and Bn, well, this corresponds to an isomorphism of SO4 and SP5. oops, no, sorry, SO5 and SP4. So this is this isomorphism, and the corresponding isomorphisms for AN, BN, and CN, if you formally write what these root systems would be for n is equal to 1, you will find the isomorphism between SL, well, for n is equal to 1, this is SL2, which is the same thing as SO3, which is the same thing as SP2. And you can check those. All right. I think probably Jethro gave the first isomorphism, that SL2 is the same thing as SO3 as an exercise. So today, there's a much stronger theorem. So what we're aiming to do is now prove that if you start from a Cartan matrix, then you can construct a semi-simple Lie algebra that has that Cartan matrix as Cartan matrix after we've made the choice of this linear functional f. And for that, well, we're going to need to identify the Cartan subalgebra of that algebra. So today we're going to prove that theorem, which is the important theorem. So theorem, which is Chevallier's theorem. Let G be a finite dimensional Lie algebra over an infinite field, but I'll just take it to be over a field K, which is algebraically closed of characteristic 0. Well, the only thing we're going to need is, well, yeah, we're going to need this. Then any two subalgebras, any two Cartan subalgebras. So let H and H prime inside of G be Cartan subalgebras. Then there exists an inner automorphism of G such that sigma of H is equal to H prime. So I need to tell you what an inner automorphism is. But the point is that any two Cartan subalgebras are conjugated. And they're conjugated by an inner automorphism of the Lie algebra G. I refuse. So if you look at Jethro's notes, Jethro's left notes in his side for you, where he takes this field to be the complex numbers, and he uses exponentials and convergence of exponentials. I refuse to do that. I'm not going to talk about an analytic ball at all. That proof simplifies it slightly. I don't really see that much. So I'm just going to give you the general proof anyways. But I need to tell you what this is. Yes, it's exactly the same theorem. If you're looking at compact Lie groups, it's much easier to prove. You have access to actual exponentials there. This is an algebraic version of that theorem. That's correct. Yeah, so under the correspondence between compact Lie groups and finite dimensional Lie algebras and finite dimensional algebraic groups, then Cartan algebras correspond to maximal tori, and this theorem is exactly what you just said. All right. So the first thing to notice is the following. So I need to tell you what this inner automorphism is. And this is going to take some time. So the first thing is what a derivation of the Lie algebra are. And this is just a subset of endomorphisms, linear endomorphisms of G. A derivation is some endomorphism, delta of G, satisfying that delta of the bracket, well, satisfies the Leibniz rule. So this is delta of A, bracket B, plus A, delta of B. So any endomorphism satisfies that, it's called a derivation. It's really it's just a derivation of the multiplication of the Lie algebra. It's easy to see that this is just a subvector space, so the sum of two derivations is a derivation. What is not entirely trivial, this is a sub-Lie algebra. So this is a Lie algebra with the bracket, with the usual commutator as a bracket, and this is a Lie algebra, this is a sub-Lie algebra of this. So exercise, check that it's a sub-Lie algebra. It's a sub-Lie algebra. Now, let's take some derivation of G. It's called nilpotent if it's nilpotent as an endomorphism. If delta to the k is equal to 0 for some k. Now, if you have such a situation, then the exponential of delta makes sense. It's well defined. This is just it's the sum of delta to the k divided by k factorial. Okay, so that's a finite sum. And it's important that I'm restricting to nilpotent derivations, otherwise I need to deal with infinite sums, and that's why convergence plays a role in those nodes. But I'll just restrict to nilpotent derivations. So once you have this thing, the claim is that this is an automorphism of G. So exercise, and it's a trivial exercise, the exponential of delta, when applied to this element of G, is the same thing as the exponential of delta applied to A, bracket exponential of delta applied to B. This is essentially just write down this formula on both sides and just collect the terms in a sum. So that means that this in particular is an automorphism of G. And remember what were automorphisms of G. So these are the endomorphisms. So these are phi, which are linear endomorphisms of G, such that phi of the bracket is the bracket of phi of A, phi of B. So this condition is this condition, and the only thing that is missing is to check that this is invertible. But that's very simple because the exponential of minus delta is the exponential of delta inverse. And again, this is just plugging in this formula. So for any nilpotent derivation of G, we get an automorphism of G. Now notice, remember that once we choose a Cartan subalgebra of G, then we get a decomposition of G as a direct sum of alpha. These were by definition the generalized roots. So I'm not assuming that G is semisimple. Okay, so these are the non-zero eigenvalues of the adjoint action of the Cartan algebra plus the Cartan subalgebra. And this thing here is the zeroth eigenvalue of that Cartan subalgebra, of the adjoint action of the Cartan subalgebra. And it's not eigenvalues, it's the zeroth generalized eigenvalue. Okay? So if your algebra is semisimple, then you know that this is a commutative algebra and that these guys are actually eigenvalues and eigenspaces and not just generalized eigenspaces. But for now, this G is just a finite dimensional Lie algebra, not necessarily semisimple. And let's just pick an element. Okay? So if you give me some A in G alpha, then the adjoint action by A is nilpotent. That's very simple because we know that we have this identity that G alpha, G beta is inside of G alpha plus beta, and here alpha could be either in this space, in this set, or 0. So that means that if you have A in G alpha, where alpha is non-zero, so here alpha is in that, then add A to the n applied to G beta, where beta could be 0 here. This is inside of beta plus n alpha. Now, these are different linear functionals for each n. And, well, G is finite dimensional. So since G is finite dimensional, this means that this is 0 for n large enough. Because, oh, in G this. Because these spaces are 0 for n large enough. Okay. So we have an automorphism for each element of G alpha. We have an automorphism of the Lie algebra G. So definition. I'll define the inner automorphisms of G as a group as the subgroup of the automorphisms of G generated by the exponentials of the adjoint actions of such alphas. And we have plenty of those. If you want to deal with the exponential of the adjoint action of elements in H, well, that's a little bit trickier because they might act semi-simply on G alpha with non-zero eigenvalue, and then you need to deal with what the hell that exponential means, which means it's an infinite sum, but if you have that the eigenvalue is an element of the field, you can write your action as some semi-simple part plus some nilpotent part, and they commute. So you use Jordan's theorem, and then the semi-simple part, you just declare it to be just multiplication by the exponential of the eigenvalue. So you can deal with exponentials of adjoint actions of H explicitly, and I'll leave it to you if you want to do that. Okay? But this is just, I'm going to take this as definition today, and it's very simple to add exponentials of elements in H. This is all we need now. By adjoint action of what? Well, but the problem is, how do you define the exponential of the adjoint action of any element? Like, no, wait. So the adjoint. So you mean without taking the exponential? Yeah. This is not an automorphism of the Lie algebra. The adjoint action of A is a derivation of the Lie algebra. That's the Jacobi condition. This is not an automorphism. To get an automorphism, you need to exponentiate. And then to make sense of this as an automorphism, then you need to tell me what the exponential is. So I told you what the exponential is in the case when the adjoint action is nilpotent, which means every element of any of these G alphas but not an element of H, because if I take an element of H and I take beta in H, then this thing remains in H. So I need to explain, or for any beta, as long as alpha is 0, this thing remains in G beta, and I cannot use this argument that is important. So I need to tell you what is the exponential of an element, of the adjoint action of an element in A. And I've already wasted so much time that I could have done it already instead of like telling you that I wasn't going to do it. But anyways, I hope that was clear. So now that explains the content of the theorem. For any two Cartan subalgebras of finite dimensional Lie algebra over an algebraically closed field of characteristic 0, there exists such an element sigma in that group that does this trick, that sends one Cartan subalgebra to the other one. In the case that you're on the complex numbers and your Lie algebra is inside of endomorphisms of a vector space, then you can replace this. The adjoint action of A now is the adjoint action by a matrix, and the exponential of the adjoint action by a matrix is the adjoint action by the exponential of that matrix. So that's something that I think might have gotten you confused, that in the case of matrices over the complex numbers, so in matrices over C, then you have two things. You have the adjoint action by a matrix X. I'm going to use letters X instead of A, just not to confuse these two cases, of a matrix Y to be X, Y, X inverse, or probably X inverse, Y, X, it doesn't matter. And you also have the little adjoint action of X of the matrix Y to be XY minus YX. So this is this, and there's a relation between these two, that the adjoint action by the exponential of X is the exponential of the adjoint action by X. Now, this exponential here and this exponential here require convergence. Okay, so this is the theorem that I want to prove, and this is going to take some time. So the first thing is, let me tell you the idea of the proof. The first thing we want to prove is that every Cartan subalgebra contains inside a regular element. So I want to prove that there exists some A in H, non-zero and regular. Because we know that once if we have a regular element in a Lie algebra, then we know that if we take the centralizer of that, well, the generalized centralizer of that element, so the spaces that have eigenvalue 0, generalized eigenvalue 0 for A, then this is a Cartan subalgebra. Therefore, it has to be H. So this theorem implies that statement. So once you prove that every Cartan algebra has such a thing, yeah, let me just let's get to prove this, and then we'll find easily this conjugation. Okay, so here's the strong theorem from algebraic geometry that I'll use, and I'll prove this later. So theorem. Let F be a morphism, an algebraic morphism, from the affine plane on K elements to the affine line. An algebraic morphism. Oops. Morphism. It's not to the affine line, I'm sorry. An endomorphism of the plane. So this means the following. So this is just a collection of k polynomials in k variables. So if you want to view in terms of points, this is, say your field is the complex numbers. So this f of x1 up to xk is just this collection of this evaluation, f1 of x1 up to xk up to fk of x1 up to xk. So this is a map that takes k coordinates and it gives you back k coordinates, and in each one of the coordinates, the map is a polynomial in the original coordinates. So that's the algebraicity of it. So the strong statement is that if you have such a map and it's non-singular at one point, then the map is dominant. If there exists some point A, which is x1 up to xk, such that the differential of f at A is non-singular. So this means that if you take the derivative of fi with respect to xj, so this is a matrix, and you take the determinant of this matrix, evaluated at the point A, this is non-zero. Then there exists a Zariski non-empty, therefore it's dense, inside of Ik, such that U is contained in F of Ik. This is certainly not true in the usual topology. If you give me a map from C to C, the image can be just contained in the disk, the unit disk. But if you give me algebraic morphisms, the image of a polynomial, which is non-constant, then it's all of the complex numbers, or it contains an open Zariski of the complex number. It might miss a couple of points. Okay, so let's take this as a black box for a second. So this is Zariski open. Let's take this as a black box, and let's use this theorem, and then I'll prove it. This is not a hard theorem, but it's just something that is not from Lie algebras, it's from algebraic geometry. So we want to apply this theorem to a particular morphism. So I'm going to cook up a morphism from G to G. Okay? So I'm going to take G, which is, I'm going to view it as an algebraic variety, as A to the dimension of G. And I'm going to cook up a map, a polynomial map, F, from G to G. So how are we going to cook up this map? So what we're going to do is choose a splitting of G as H plus this GH, G alpha. So this is the composition with respect to the adjoint action of H. So we're going to choose a basis of each one of this, of all of this space. So choose a basis, AI, for this space. The only condition is that you're going to require that each one of these AIs is in one of the G alphas for some alpha. So for example, you take a basis of G alpha, you extend to a basis of G alpha 1 plus G alpha 2, and you extend it to get a basis of each one of these spaces. Take the union of all of those spaces. So that gives you a basis for this sum. And every element of G, therefore, can be written uniquely as, so every element of GA can be written uniquely as some H plus the sum of, oh, alpha is huge, it's horrible, lambda I, AI, where H is in the Cartan subalgebra and the lambda I's are in your field. Okay, so we've chosen a basis of this part, and I don't care about picking a basis of H. So that's going to give me this map here. The map here is as follows. So you take F evaluated at H plus this sum, lambda I, AI. Again, any element of G can be written uniquely in this form. And I'll declare this to be the exponential of minus lambda 1 A1 times the exponential of minus lambda 2 A2 times the exponential of minus lambda R AR. All of this evaluated at H, where this sum goes from I is equal to 1 to R, and R is the dimension of G minus the dimension of the Cartan subalgebra. Okay, so why did we go through all of this trouble? Each one of these AIs is in one of the G alpha I's, so therefore the adjoint action, oh, this is the adjoint action of each one of these guys. So the adjoint action by each one of these guys is nilpotent because they are not in the Cartan algebra, they are in one of the G alphas. So each one of these exponentials is well defined. So this is a composition of elements of composition of automorphisms which are inner automorphisms. So this whole composition here is inside of the inner automorphisms of G. And this is applied to an element in the Cartan subalgebra. So this looks like an element sigma applied to an element in H. And this should be like the sigma that I'm trying to look for in the Chevalier's theorem. Second, that thing is polynomial. When I've chosen this isomorphism of G with an affine space, then the coordinates in G are those lambda I's and whatever coordinates that I choose for this H. And you can see that these exponentials, these are finite sums of lambda I to the J times the adjoint action of this guy to the J. So lambdas, which are the coordinates of this map, appear polynomially in this product. These are finite sums. These exponentials are finite sums, and therefore these lambdas appear polynomially. So this map F is a polynomial map from G to G, and I can apply that theorem. So I need to check that the differential of this guy is non-zero at some point. Okay? So want to check the conditions of the algebraic geometry theorem. So want to check that the differential of F at some point A is non-zero. Well, the determinant is non-zero. So let's find such an A. And what I'll do is I'll apply this for an element A, which is going to be inside of the Cartan subalgebra. So this A here is going to be inside of the Cartan subalgebra. Let's see what it is. So let's take the differential of F evaluated at a point in the Cartan subalgebra. So let's evaluate it at H. Oops. Let's say A. It doesn't matter. At A. So now this is a linear endomorphism. So this goes from the tangent space. This goes from the tangent space at A of G to the tangent space at A of G. Well, actually at F of J of E. But this thing here is isomorphic to G. This G was just an affine, it's a vector space. And this is isomorphic to G. So this differential I can view it as an endomorphism from G to G. Right? So this is all A K for some K, the dimension of G. And I want to understand what is this thing. And it's very simple. So if you have a linear space and you have a polynomial map between this space, then how do you compute the differential? Well, you evaluate this as an element to an element of G. So the df at A evaluated at a general element on G, well, this is something like this. This is something, well, let me write it first. At B, this by definition is you take f of A plus t times B and take the derivative of this with respect to t and put t is equal to 0. That's how you compute derivatives at a point. Okay? So now the general element B, it's written as H plus the sum of lambda I AI. And my element A, I'm going to choose it to be in the Cartan subalgebra. I'm free to choose A whatever I want. I'm going to choose it to be in the Cartan subalgebra. H is in the Cartan subalgebra. And these AIs are my basis for the remaining of the Lie algebra that I've chosen. So this thing here looks like the derivative with respect to t at t is equal to 0 of f evaluated at A plus t times H. This is the part that is inside of the Cartan subalgebra, plus the sum of t lambda I AI. And then I go and I look at what is my definition of f. My f was very explicit. It was a polynomial map which was very explicit. My f was given like this. So it's something evaluated at A plus th. And what is what I'm evaluating it? So this is the exponential of minus lambda 1 adjoint action of A1. And there's a t. Up to the exponential of minus t lambda r adjoint action of AR. And all of this needs to be evaluated at the part that is in the Cartan, which is A plus th. And then out of that, I need to take the derivative of this with respect to t and put t is equal to 0. Okay? So the exponentials, these are just polynomial guys. So it's enough for me to expand this up to order 1 in t. Okay? So what is the constant term here in t? Well, the constant term is just, this is all the identity, and I just get the identity here. So the constant term in t is A. So this thing here is A plus something. Now I need the linear term in t. So the linear term in t is going to be, out of this sum, I need to pick the linear term in t for one of these factors. And then the constant term for all of the other ones. So that's going to be a sum of, there's a minus sign, because there's a minus here. And I'm going to have t because I'm looking at the linear term. And I have the sum of lambda I adjoint action of AI applied to this element, but I'm taking the linear term in t, so this element is in A. So this is applied in A, to A. So that's when I choose linear term in one of these exponentials and constant term here. But there's one extra term, which is take the identity of all of these guys and apply it to t times h. So I have plus h. And then the rest is of order t squared. So now I take the derivative of this thing with respect to t. So this guy dies, and I put t is equal to 0. So this is h minus the sum of lambda I AI bracket with A. And remember, since we wrote B as H plus the sum of lambda I AI, this is the same thing as H plus B bracket A. The other way around, A bracket B. So this is H plus A bracket B. Okay, and this is the differential of F at the point A evaluated at the point B. No, there's something wrong. Ah, shit. Let me call this space, this guy here, C. So this is H plus the sum plus A bracket the sum of lambda I AI. I just flipped this 2, changed this minus sign, and took the sum inside. So this thing here is what I've called C right there. So this is H plus AC. And this is the differential of F at the point A evaluated at the point B, which is H plus C. Okay, so this differential takes H, if I restrict this thing to H, is the identity of H. It takes H to H. Okay? Takes H to H. C is equal to 0. And on the other hand, the adjoint action of A is in H. On the direct sum of G alpha, where alpha is in delta, has non-zero eigenvalues. Okay? So it has non-zero generalized eigenvalues. So this thing is, the adjoint action of A on that direct sum is invertible. So this thing here is invertible. So this thing restricts to the other summand to something invertible. So it means that this differential of F at the point A looks like the identity on H, 0, on the piece that is H, and it looks like something invertible, 0, on the other piece. So this thing here has non-zero eigenvalues everywhere. So this is non-singular. So that means that this map F has a non-trivial Zariski open in its image. By the theorem, there exists a non-trivial Zariski open inside of G in the image of F. Now the image of F consisted, all of them, so the image of F consisted of elements of the form sigma applied to H. F was just exponentials of adjoint actions of elements in G alpha, so these are all elements in the inner automorphism group of G, and they were all applied to the Cartan part of the elements. So what we're saying is that if I look at the set of the form sigma of H, where sigma is an inner automorphism of G, then this set contains a non-trivial open Zariski inside of G. Okay, so I can apply it, and that works for any Cartan subalgebra H. So I can apply it for H and H prime. So I have an open for H, and I have another open for H prime. So I have U for H. I have another open U prime for H prime. So these U's are elements that are conjugated to H by an inner automorphism. These U primes are elements that are conjugated to H prime by an inner automorphism. These are open Zariskis that are non-empty inside of G. And I also have the regular elements of G. And we've seen, I hope we've seen. So Jethro defined what regular elements for a Lie algebra are. So this is the discriminant of the element is non-zero. That's a polynomial equation. So this is also a Zariski open inside of G. So we have three opens that are non-empty. The field is infinite. These things are all dense, so their intersection is non-empty. So that means that there exists an element here, A, in the intersection of all these three things. In particular, is a regular element, which is here. So that means that there exists some sigma that sends A, or sigma inverse, if you wish, is in H. And it's here, so this is some sigma prime of A that is in H prime. So that means that there exists an element in H, which is regular. So the other observation is that if A is regular, then this is regular. And this is regular. So in particular, H has a regular element, and H prime has a regular element, and this is the centralizer of A inside of sigma prime of A inside of A prime, and this is the centralizer of sigma of A inside of G. Okay, and then the statement of the theorem is proven by checking, therefore, that, what did I need? H to H prime. So you check that sigma prime composed with sigma inverse needs to send H to H prime. Why is that? Well, because let's take an element in H, which is sigma of A. This is a regular element which is inside of H. And it takes this regular element, when you apply sigma prime composed with sigma inverse of this is sigma prime of A, which is inside of H prime. So it sends this element in H to this element in H. In particular, it sends the centralizer of this element in H to the centralizer of this element in H. And the centralizer of this element is all of H. And the centralizer of this element is all of H prime. Okay, so that's the proof of the theorem. All right, so we have this Chevallier's theorem modulo this algebraic geometry statement that I haven't proven. So let's prove that statement. I have a little time, so I'll do that now. Okay, so I want to prove that if I have an algebraic map from affine space to affine space that is non-singular at a point, then the map is dominant. It has, its image is dense on the affine space. It contains a non-empty Zariski open inside of the affine space. Okay, so the first observation I'll make is that if you have such a thing, so let's suppose that the image of F, right? So remember, we have a map from AK to AK. And let's suppose that the image of F does not contain any Zariski open. So if it doesn't contain any Zariski open, then there's some subvariety here where this map factors through. There's some subvariety of AK where this map F factors through. So that means that this image of F is all included in some subvariety of AK. If it doesn't have an open Zariski, then it's included in some closed space. And that means that, well, this can have any codimension, but the closed ones inside of AK, they're cut out by polynomial equations. So in particular, there's a bunch of polynomials that are 0 on the whole image of F. I can just choose one of them. So I can assume that this Z is a hypersurface inside of AK, but I just choose one polynomial. So this means that there exists some polynomial, F, which is a polynomial in K variables, x1 up to xk, such that F evaluated on the components of F, F1 up to Fk, is equal to 0. That means that this little f is included, the image is included in the zeros of this polynomial. In particular, these fi's are algebraically dependent. And conversely, if there's no such polynomial, then that's the definition of that these fi's are algebraically independent. Okay, so if there's no polynomials where these fi's vanish, so there's no polynomial equation satisfied by these little fi's, then these fi's are algebraically independent over this ring. Okay, so I want to prove that this cannot happen. So if this cannot happen, then, well, I want to prove that this cannot happen. So if this were to happen, then I can just look at the differential of this map. And this is, by the chain rule, the differential of f, this is given by a sum of derivatives of f with respect to some coordinates. So x, I'm going to call it yi, from I is equal to 1 up to k. And this is multiplied by the derivative of the ith coordinate here, which is fi, with respect to xj. And the sum is over I here. And this thing is 0 for every j. That's just the chain rule. This is the derivative of this thing is constantly 0. And this is the differential of f. This is the matrix of the differential of f. And this is the matrix of the differential of big F, which is just a vector. So this is a vector whose all of its components are 0. So this goes from 1 up to k. Okay? But the space where the differentials of this guy is non-zero is an open Zariski. And if I am assuming that this f is a non-trivial polynomial equation, it's not f which is 0, so this is a non-constant differential equation, non-constant polynomial equation, then this thing is a non-empty Zariski set. And this guy, it's also, I'm going to look at the opens where this guy is non-singular. Non-singular. Well, this is, again, the non-zero values of the determinant of this matrix. So that's a Zariski open. It's the non-vanishing of a polynomial. These are polynomial equations. The determinant is also a polynomial. Therefore, this is the non-vanishing of a polynomial. And this is non-empty as well, because I know that there's one point where this determinant is non-zero. So there's something in the intersection of these two. And that's absurd, because, well, I'm just saying that this guy has a non-zero eigenvalue in that intersection. So this cannot happen. So we know that the fi's are algebraically independent. And if they are algebraically independent, it means that we have this extension. Okay? So we have this f, the k, x1 up to xk. And inside of this guy, we have k of f1, fk. And now we just check that this is an algebraic extension of this field, of this ring, I'm sorry. So we have an algebraic extension of, this is an algebraic extension of this ring, and they are both over the field k of transcendence degree k. I'm using too many letters k, but they're both of dimension k. So that means that this has to be a finite extension. So that's a finite algebraic extension. Oops, sorry. So we get now as extensions of fields now this is a finite algebraic extension. Extension of fields. Okay. But the fi's were algebraic over the xi's. They satisfy some algebraic equation. So what you can do is look at the polynomials. I have just enough time. Yeah, that's correct. Okay. So what I claim is that, so we can look at some polynomial equation satisfied by each one of these fi's over, no, I'm sorry, by each one of these xi's. Since the extension is algebraic, then each one of the xi's satisfies a polynomial equation. So it's an integral extension. So each one of these xi's needs to satisfy a polynomial equation over the fi's. Well, but these are rational functions, so it's a polynomial over this ring. So we can just clear denominators on those polynomial equations so that now these xi's actually do satisfy a polynomial equation over the fi's. So let's take those polynomials to be pi's. From I is equal to 1 up to k. So, well, let me call them pi bar. So now take the leading coefficient. Let pi be the leading coefficient of this pi bar. Pi bar. So now that's a polynomial. For each xi, you have such polynomial, pi. And now claim, if you look at the intersection of all these pi's non-zero, so these are non-trivial, since this is the leading coefficient, this is a non-trivial polynomial, it's a non-zero polynomial. So these are all the intersection of these things, which are non-zero polynomials, so these are all Zariski open. You take the intersection over all I, this is some u, and that's in the image of f. And the proof of this statement is trivial. So the proof of this is, you take an element here. Let's say you have some A inside of here. So each one of these PIs is non-zero. So PI of A is non-zero. So this means, well, you have an evaluation. First of all, we have the following evaluation. From F1 up to Fk to K, which is the evaluation at the point A. You just send Fi to K, to Fi of A. So this sends Fi to Fi of A. But notice that each one of the PIs also goes to PI. So each one of the PIs, when I evaluate at A, goes to something non-zero. So if I have that each one of the PIs, which is a polynomial, goes to something that is non-zero, then I have that you can extend this to the localization. On the other hand, this extension here was defined in such a way that this is an integral extension over this ring. This extension was integral, was an integral extension. So we constructed these PIs in such a way that, well, this guy was a finite extension. So if we have this thing like this, and this field is algebraically closed, then we have an extension like this. So that's an easy exercise in commutative algebra. This guy exists because this extension is integral. And once you've proven that this map exists here, making this diagram commute, then you just evaluate this map at A. And you're going to find out that this is just F of A. So out of this, you prove that A is in the image of F. OK. So that's the horrible theorem of, well, the theorem is beautiful. It just required this horrible construction that we used basis of the Lie algebra everywhere, and we constructed this polynomial map. So we made a lot of choices here. To construct this map F that we ended up applying this theorem, we've made the choice of a basis. So the choice of a basis AI to write this every element and then write this F of an element H to be the exponential of an element of the form H plus the sum of lambda I AI to be a product of exponentials applied to H. But after the fact, the theorem is beautiful. It says that if you give me any two Cartan subalgebras, they are conjugated. Notice that they are conjugated by an inner automorphism. There are outer automorphisms of Lie algebras. So look at counterexamples to this theorem where K is not algebraically closed, for example. Let's look at SLN. This was one of the exercises typically. So this is a typical problem of test. So take SL2, but instead of over the complex numbers, take it over the real numbers and try to find different Cartan subalgebras that are not conjugated and that they might be conjugated by an outer automorphism. So, question, what are outer automorphisms of SLN? All right, so next time I'll exploit this by, well, we're going to prove that you if you give me a carton algebra, then there exists a unique semi-simple D algebra with that carton algebra. I think that's next class, and hopefully that's my last class. I don't remember if I have 1 or 2 more classes.